Okay, in this video right here, let me shrink my screen. Let me get my image made over and let me share my screen. And so in this video, we want to go over how do you find the area between two curves that have possibly multiple intersection points. And what happens when they have multiple intersection points, so I just drew a picture of a g function like this and an f function like that. And you can see there's clearly area that's bounded between these two curves. I have the first area, and I have the second area. But look at the small little difference. The height function is different. The roll of the top function here is f. And the bottom is g in area 1. In area 2, the bottom function is f, and the top function is g. The rolls of the top and the bottom have changed. So what we need to do, if we're trying to find the area underneath or bound between these two curves, we have to reflect that, and we have to figure out that intersection point, because that's going to end up splitting the integration regime, because here, f is the top, g is the bottom, so I'm going to integrate from a to b, but then I have to switch the roles, g of x and f of x, and I have to integrate from b to c. So the extra step in here is going to be, you have to have a good picture of f and g to be able to determine analytically or graphically where these functions may intersect. So let me give you a practice problem. So suppose I have this cubic function, let's call it f of x, and I have this quadratic, I'll call that g of x. The first thing we have to get, if we're going to render a drawing of this without using Desmos or a calculator, which is what you need to be able to do, we have to figure out, do these functions intersect, and if so, where? If they only intersect at two locations, that means they only have always one of the functions is the top, the other function is the bottom. And I don't have to do something like this. But if there's more than one or more than two intersection points, okay, then I'm gonna have to do something. Think about what we just did where we had bounded between two curves. There were always just two intersection points. This is the case when you have 3 or 4 or 5, and you have to look at your domain and see what's the role of the top and the bottom function to be able to figure out what the integrand should be. So there's some algebra that's done before we start this process. Let me get my almost a lot of focus there. Okay. So first question you got to ask, when does my function intersect g of x? And so I'm going to set the two equations equal to each other, and I'm going to simplify accordingly. So I bring over the x squared, that cancels. I bring over the 2x. I have 3x cubed minus 12x. I can factor out a 3x, and I have 3x times x squared minus 4, and I find 3 intersection coordinates, -2, 0, and 2. And what I want you to look at is we're going to make a little grid here. And I'm going to put in the top part, who is the top function and who is the bottom function in the bottom part here. So I'm going to look at my domain from -2 to 2. We're trying to figure out what's the top function between -2 and 0. Well, I can evaluate this function in between 0 and 1. And if I evaluate, say, at -1, I can then see if that value is greater than the value at g. And it is, so I'm going to say the top function between 0 and -2 is f of x, while the bottom function is g of x. Likewise, if I look at this interval here, let's take x equal to 1. F of 1 would be 3 minus 1 minus 10. That's negative. But here, I got -1 plus 2. That's positive. So bottom function is f, the top function is g, which means I have to integrate here from -2 to 0, f of x minus g of x, plus the integral from 0 to 2, g of x minus f of x. And I work through that analysis. Well, let's get a picture of this using Desmos. So what I've drawn is, here's f of x, my cubic function, and here's my quadratic. And you can see there's definitely some area that's bounded between these two. You can see it right there, and here, and there. So you can see there's 3 different regions. I have the first integral that I have to render. The top function is blue, the bottom function is black. Okay, and then I have the other region, which I have to integrate from 0 to 2, and the bottom function is blue and the top function is red. So in order to be able to get that integration result, you have to separate the integral into two different ones and then integrate it accordingly. And that's what we're doing in this process. Once we have this set up, we can then simplify. In this case, we have just product rule, or sorry, power rule that we're using to find our antiderivatives and to use a fundamental theorem of calculus. And it works out to an area of 24. Now, so this just adds an additional step in your calculation right here. When do these functions intersect? And if it happens in more than 2 locations, then you have to make this number line to see what the top and the bottom functions are and to proceed forward. So get started in the homework in this particular one. This is section 7.1b, and that homework assignment has already been uploaded on the Google Classroom.